At the San Diego Supercomputing Center booth, I have met Venkat and Rick, and with a very interesting visualization of galaxies. And I asked them what is special about this simulation, and they told me one side there is you creating a lot of data, and then there is you enabling him to visualize this data. And it's sure one of the biggest problems we have today in supercomputing is difficulty to handle such a large amounts of data and to visualize them. So I asked you two to have a short Q&A discussion between you two about the challenges you are having, and leave you alone and go to the other side, please.
Thank you.
So, I'm Rick Wagner from the San Diego Supercomputer Center, and we're here at SC11 in Seattle, Washington. One of my roles as a scientist is to help with simulations of very large numerical scale. The videos you've seen earlier of the galaxy formation are huge. They're 256 gigabytes for one small subset of the field, and they grow to terabytes for the entire one. And the way we traditionally do this is to write these terabytes for each snapshot to disk and then come back and analyze them later. And it's quite a challenge, and we'd really like to avoid this pattern because it's not sustainable in the future.
Hi, I'm Venkartram from Argonne National Laboratory. I'm an assistant computer scientist working on extremely large-scale data sets and how to analyze these data sets as it's being produced by the simulations. So one of the biggest challenges as we go towards next generation simulations is that I/O is not keeping up with the rate that the compute capabilities is growing. So we are working on efficient infrastructure and software infrastructure too, on how do you reduce the amount of data being written to storage systems by performing analysis as well as visualizations as the simulation is progressing. So this way it helps transform the data into insights faster than being written to storage.
So one of the questions I have is the scale of our simulations at 3200 cubed. It's using tens of thousands of processors, and I would like to not interfere with our code as much as possible. So I know that you had a technical paper of this program. Is it showing the kind of results where I can trust that if Enzo's current data patterns were kept, how do I know that I can still take advantage of this and preserve my data integrity and get the analysis done without slowing down the code while it's running?
Sure. Thanks for bringing that up, Rick. So at the SC technical program this year, we published our work on Glean, which is I/O acceleration and simulation time analysis framework, wherein we have scaled simulation time analysis and visualization all the way up to 160,000 cores of our Blue Gene P infrastructure at Argonne National Labs. That is the entire Intrepid Blue Gene P supercomputing system. So what we've done is we've worked on mechanisms by which we can make non-intrusive integration with the simulation so that we can buffer the data, we can integrate with the simulation without modifying a single line of the code. We can buffer the data, we can stage it, and we can write it out, maintaining the integrity of the data formats that you've produced. We have various ways to validate and verify that it is indeed what we are writing it out.
So is this buffering process in any way faster than the current I/O? Because Enzo, we spend a lot of time optimizing the I/O to be as high performance as possible. So slowing down the code even more would not be attractive.
Sure. So for Flash, which is an astrophysics simulation that runs on our supercomputing systems, we've achieved about a 350-fold improvement to write HDF5 data sets to the storage system.
That's pretty bold. Okay, I still want to check out the technical paper.
You should definitely check out our technical paper.
Okay,
Thanks so much.